Welcome to Lightning Bolt's Boltology 101 course. Here you will learn a wide array of different types of fastener knowledge. I'd like to welcome you to the Thunder Threads fastener training video. This video has been designed as a robust yet introductory guide to the fastener industry. Throughout this video, you will learn a lot about the primary standards that govern the fastener industry and how to properly identify the many different types of fasteners that exist. You will also learn about internal and external threads and a variety of materials that commonly fasteners are made from. We will also cover fastener manufacturing, heat treating, as well as the common corrosion-resistant coatings and platings. Lastly, we will then discuss how to properly order fasteners and discuss the different types of vendors. In addition, we will explain the differences in VMI and CMI and give an overview of the different types of customers that buy fasteners. Fastener standards, which some call specifications or specs, are essentially the rules that fasteners are manufactured and ordered by. Standards give manufacturers and buyers guidelines for the many different aspects of fasteners, which are primarily either dimensional requirements, mechanical requirements, or chemical requirements. Oftentimes, these requirements will be stated as a tolerance in which a value with a min and max is acceptable. The most common standards include SAE, ASTM, ASME, and several of the more popular metric standards such as ISO, DIN, and European Union. Others exist like military specs and NACE, which we will not be covering in this tutorial. True to its name, the SAE specification is commonly used in heavy equipment, tractors, trucks, and machinery. One of the most common threaded fasteners in our industry, grade 5 and grade 8 hex cap screws, are governed by the SAE J429 spec. However, if you're dealing with structural steel or piping, you'll probably be dealing with fasteners that fall within the ASTM specifications, such as A325 structural bolts, which is commonly used in fastening structural steel together, or the ASTM A193 specification, which is more commonly used in B7 studs to fasten together pipe, where ASME is a standard that typically dictates dimensional requirements and tolerances. The metric world is heavily governed by three popular and often overlapping standards. These include the ISO, the International Standards Organization, the German DIN standard, and the European Union standard. Although we'll cover these items in more detail later, it's important to understand that even common fasteners have 6 different items to properly identify them. This includes the nominal diameter, the thread pitch, the length, type of product, the grade or material that the fastener is made of, and any anti-corrosion coating or plating. Keep in mind that due to the Fastener Quality Act, all fasteners except for low-carbon steel such as grade 2 or A307 are required to be marked with the manufacturer's head mark and also the designation indicating what grade or material the fastener is made of. Most people don't realize that fasteners are actually highly engineered products that are designed for certain uses. As mentioned previously, some standards are focused towards different applications, such as the SAE spec focusing more on automotive and heavy equipment, and the ASTM spec that focuses more on structural steel and piping applications. It should be understood that some fasteners, although under different specifications, share very similar mechanical properties. For example, if you focus in the middle column, I'll explain that the tensile strength for a grade 5 hex cap screw, an A325 structural bolt, a B7 stud, and a metric class 8.8 bolt is almost identical. They're simply engineered under different specifications and oftentimes for different applications. However, we will discuss later how although the tensile strengths of a grade 5 and A325s are nearly identical, the A325 structural bolts were definitely engineered to make them much more better suited towards fastening structural steel. So to say it once again, the SAE world handles a lot of fasteners that are really more used in heavy equipment and machinery, whereas the ASTM standards focus more primarily on piping and structural steel. Here is a brief chart that compares the mechanical properties of grade 2, grade 5, and grade 8 materials to that of 18.8 stainless and class 8.8, which is a metric material designation. Again, all fasteners except for grade 2 low carbon steel must be marked with the manufacturer's stamp as well as the grade or material designation. So you must know that a grade 5 bolt will have 3 marks and a grade 8 bolt will have 6 radial marks. Imagine if a friend asked you to recommend a high-strength bolt to put in his tractor. First of all, we don't like recommending anything since it actually opens up to more liability. But one might look at this from the bottom of the chart and say, oh, well, stainless steel is better than anything else. That really isn't the case. I'll definitely be covering more in detail as to meaning and differences of proof load, yield strength, and tensile strength later. However, if you compare the tensile strength for a grade 5 bolt, which is the minimum force at which a fastener will break, and the tensile strength for an 18/8 stainless steel bolt, they're about the same. Therefore, a grade 8 bolt would be a much stronger bolt than a stainless steel bolt and better suited for a tractor. Charts like this can summarize specifications and also explain, for example, that just because you get something in stainless, it doesn't mean that it's better. At the end of the day, fasteners are highly engineered items whose grade and material needs to be properly fitted for the application that it's being installed. Before we dive in, I want to just give a basic overview of the different types of products we'll be covering. We'll first start with externally threaded fasteners and then go into screws. Secondly, we'll cover internally threaded fasteners like nuts and then into non-threaded fasteners such as washers. We'll then conclude with other items that are commonly found in bolt bends like pipe fittings and electrical terminals. So let's first talk about externally threaded fasteners. We'll start with hex cap screws and hex head bolts. So what is the difference between them? These terms are often used incorrectly and interchangeably, however, they are different. Although they look very similar, the variations between these fasteners are quite significant. Generally speaking, hex cap screws are used in a more precise application with tighter tolerances, whereas hex head bolts are often specified when the mechanical properties are more important than the dimensional tolerances. Like in the construction industry, SAE J429 is the spec that covers grade 2, grade 5, and grade 8 hex head cap screws, whereas ASTM A307 is a common hex head bolt specification. Here you'll see the IFI, which is the International Fastener Institute summary for hex head cap screws. As you can see, it references ASME standards B18 2.1 in the top right, which is actually the spec that covers the many dimensions required for both hex cap screws and hex head bolts. To understand the differences between hex bolts and hex head cap screws, one must understand the specifications that govern them. This chart indicates that hex head cap screws can range in size from 1/4 of an inch up to 3 inches in diameter. Albeit, hex head cap screws are very similar to hex bolts. However, they do differ mostly in that hex head cap screws manufactured to tighter tolerances than the corresponding hex bolts. For example, let's compare the tolerances, also referred to as mins and maxes, for the diameter of a 1-inch diameter hex head cap screw and hex bolt. Here you will notice that the maximum body diameter for a hex head cap screw is 1 inch. However, the same ASME specification gives the maximum body diameter for a 1-inch hex bolt to be 1.022 inches. Not only does that extra precision for a hex head cap screw come at an added cost, but that extra 22 thousandths of an inch can definitely be enough to cause fit issues in certain circumstances. Other differences between hex head cap screws and hex bolts can be a little bit more obvious. For example, hex head cap screws have a flat washer facing forwards underneath the head, which is usually made by cold heading in high production runs. Hex head cap screws are also most commonly found in grade 5 and grade 8 out in the field. On the other hand, hex head bolts do not have a washer facing underneath the head. Hex head bolts are more commonly made via hot forging and are often made out of carbon steel specifications like ASTM A307 and F1554, which is commonly made for anchor bolts. We'd like to discuss some additional notes about both of these products. Of course, like all hex head products, they are measured from underneath the head to the end of the threads. I like to give you a rule of thumb to help you determine the amount of threads on a hex head cap screw. For those that are 6 inches in length and shorter, you double the diameter and add 1/4 of an inch. For those that are longer than 6 inches, you simply double the diameter and add 1/2 an inch. For example, a 1/2x3 hex head cap screw will have 1.25 inches of threads. Another interesting rule of thumb is that most bolts that are longer than 10 inches will have 6 inches of threads. This is pretty common with anchor bolts. Bolts that are fully threaded are also called tap bolts within the fastener industry. Another type of externally threaded fastener is a stud bolt. Stud bolts are commonly made by cutting them from all thread rod, which is typically 12 feet long. Since stud bolts do not have a head, they definitely require two nuts for assembly. Aside from welding pipe together, studs are commonly used to join pipe at flanges. It should be noted that there are two different ways of determining the length of studs: overall length and first thread to first thread. Lightning Bolt Thunder Threads has chosen to measure studs according to their overall length, but it is handy to understand that two different ways of measuring lengths do exist. Studs can come in a vast array of grades and coatings. However, the most common stud bolt for flanging together pipe is ASTM A193 Grade B7, which of course you will always mate with an A194 Grade 2H heavy hex nut. To make B7M studs, you'll actually start with a grade B7 material and then reheat treat it, thus the M stands for modify. B8 and B8M is actually completely different in that B8 is a 304 type stainless steel equivalent and B8M is a 316 stainless steel equivalent. Much like peas and carrots, B7 studs should always be mated with 2H nuts. We'll cover coatings later in this video, but one thing you should always mate like coatings with like coatings. For example, if you have a Teflon coated B7 stud, you should always mate it with a Teflon coated 2H nut. Here you will find a chart comparing several of the more popular ASTM grades. As you will notice, each grade is designated for different applications as they have different tensile strengths and service temperature ranges. It is also important to notice that many charts like this will also tell you what grades of nuts are acceptable to mate with the corresponding studs. Chemical plants move liquids and gases via a complex network of pipes that are automated with valves. So to connect the pipes together, you have two different ways. You can either weld them together, or you can bolt them together. So as you can imagine, industrial plants use a large amount of fasteners. To make things easier for pipe fitters, flange charts exist to quickly determine the size and quantity of fasteners needed to assemble a flange. For example, if you're assembling a 150-pound, 12-inch flange, you would use 12 pieces of a 7/8x4 stud and 24 nuts. Just be aware that sometimes items can interfere with your results, like the shape of the flange, the thickness of the gasket, and whether the chart is indicating stud lengths measured first thread to first thread or an overall length. Double-end studs, although much less common than fully threaded studs, can also come in the same variety of materials. The main difference is that upon order you simply need to know all the dimensional information. So when communicating the dimensions of a double-end stud, you need to know the diameter, the overall length, and the number of inches you want threaded on side A and on side B. A very common fastener in the construction industry is the ASTM A325, which is a structural bolt that was designed for the sole purpose to hold together structural steel. This is the steel that holds together most large buildings, high-rises, and chemical plant pipe racks. ASTM A325 and A490 are the two most common structural bolt standards. Structural bolts are specifically designed for use with heavy hex nuts in the connection of structural members as opposed to tapped out holes. The nuts for structural bolts shall conform to the ASTM A563 spec. The following chart exists to assist in proper structural nut selection. As you can see, grade C and or grade DH heavy hex nuts are the proper nut that you'll want to mate with the A325 structural bolt. However, one should realize that ASTM A563 also allows grade 2H nuts to be mated with A325 structural bolts. The flat washers to be used for structural applications shall be ASTM F436. Therefore, a standard USS pattern flat washers are unacceptable for structural steel applications. When looking at the mechanical properties of bolts, it appears that the ASTM A325 and the grade 5 hex cap screws are nearly identical. And also the A490s are nearly identical to the grade 8 hex cap screws. This begs the question, should an SAE J429 grade 5 be substituted for a structural bolt? The answer is no. This is also the case when comparing a grade 8 to an A490. They're just not the same, and here's some reasons why. First of all, when compared to grade 5 or grade 8 hex cap screws, A325 and A490 bolts are produced with a heavy hex head configuration. This provides a wider bearing surface over which to distribute the load. Grade 5 and grade 8 hex cap screws are produced to standard hex cap screw configurations and therefore cannot distribute the load as much as needed for structural applications. Secondly, The shank length, which is the non-threaded portion of the body on A325 and A490 bolts, is designed to be greater, which is shorter thread lengths than your standard hex bolt or hex cap screw. Remember, the weakest section of any bolt is actually through the threaded region. Minute design changes such as this can create stronger tensile connection. So as you can see in the top left-hand corner, on the left is a hex cap screw and on the right is a heavy hex pattern of an A325 structural bolt. The picture beneath it actually shows the difference in shear strength between a hex head cap screw, which is on the right, having more threads, and the hex head bolt on the left. If you can imagine, the forces applied in structural bolts are completely different than those found in piping applications. For example, the forces in a flange are actually pulling parallel with the length of the bolt. In contrast, structural bolts are actually dealing with a force called shear force. In shear force, they're actually going in opposite directions that are perpendicular to the length of the bolt. The chart on the bottom shows the differences of shear force when applied to a hex bolt versus a hex cap screw. As we mentioned earlier, the threads are the weakest part. Thereby having structural bolts that do not have threads within the plane of the shear force makes them a great fit for structural applications. Oftentimes, drawings and blueprints indicate the structural bolt with an X or an N designation. The X indicates that the threads are excluded from the shear plane, whereas the N designates that the threads may be included in the shear plane. Due to the extremely high volume of structural bolts used on job sites, the fastener industry is always looking for innovative ways to make the assembly of structural steel faster and more efficient. Tension control bolts are the type of structural bolts that require a special torque gun during installation. When the bolt is properly tightened, the tip of the bolt breaks off and stops the torque gun from any additional tightening. This helps contractors by minimizing the amount of equipment needed to quickly achieve proper torque, while providing an easy visual indicator for inspectors. Click on the link below to watch a video about tension control bolts and DTI squirter washers. The next externally threaded fastener we will discuss is elevator bolts. So where would you guess that elevator bolts are used? If you answer they are used on elevators, you're partially right. Because although they are not used in conventional elevators that we may use in high-rises and office buildings, elevator bolts are in fact made to be used on bucket elevators. Bucket elevators use a series of buckets that are fastened to a circulating belt to help move solids from a lower elevation to a higher. These are commonly found in grain elevators and other applications that are lifting solids to a higher level. Many of Louisiana's grain elevators receive soybean, corn, and grain via barge and rail car, and subsequently warehouse them in huge silos waiting for large ocean-going ships to arrive and export them to another country. It should be noted that elevator bolts have a flat head and a square neck. Therefore, the flat head fits flush with the bucket and no screwdriver or wrench is needed to turn the head of the bolt. This is the case since there is a square neck on elevator bolts, they fit into a square hole that's drilled into the bucket. Although a standard elevator bolt is pictured here, they come in a variety of different patterns, with some having sharp prongs underneath the head. Similar to elevator bolts, plow bolts have a flat head and a square neck. Like their name states, plow bolts are actually used on plows and are also called blade bolts and scraper bolts because they're used on bulldozers and heavy equipment to hold the blades on. Carriage bolts are actually very similar to plow bolts in the sense that they have a square neck. They're commonly found in zinc-plated, hot-dip galvanized, plain, and also in stainless steel, and used in a whole variety of different purposes. The next type of externally threaded fastener we will discuss is the lag screw. These screws are typically found with a hex-shaped head, and are named such because they have a lag-style thread, which is a coarse, sharp thread designed to grip into wood. Lag screws are often found in fences, decking, and crating used for shipping large equipment. They are most commonly found in carbon steel, either zinc or hot-dip galvanized, and also in stainless steel. Anchor bolts can actually be a world of themselves. Before you are 6 different types of anchor bolts used in holding down buildings, equipment, and towers to the concrete slab they sit on. The type A is commonly referred to as an L anchor. As you can tell by the chart, the length of L anchors are measured from the inside of the L or hook. The other types shown here are essentially double-end studs with different assortments of nuts, washers, square washers, and the option of having them welded on. Anchor bolts are commonly made from carbon steel and then furnished to the contractor either in plain finish or in hot-dip galvanized typically. The stage of a construction project that is dealing with moving dirt and pouring foundations is called civil construction. Therefore, many civil contractors spec out anchor bolts on industrial projects that are very custom and can become quite large and expensive. Before you is a few pictures of anchor bolts. Overall, these bolts are usually pretty large and heavy, and when installed are almost completely submerged by concrete, except for the threads that are protruding above the surface of the concrete. As mentioned previously, anchor bolts are almost always either plain finish or hot dip galvanized. It is important that care is taken during the hot dip galvanizing application, because if you end up with a lot of galvanized stuck in the threads of the anchor bolt, you won't be able to put a nut on it. You can imagine how upset a customer would be if they have their anchor bolts already poured into place and they can't get nuts on them. Imagine having a piece of important machinery that is interconnected with other large, vibrating machines. I'm sure we'd all agree that you wouldn't want these machines to start vibrating and moving across the floor of the warehouse. For this reason, you would want to anchor them to the concrete foundation below them. Before you is two of the most common methods to anchor equipment and machinery to pre-existing concrete foundations. Common applications include anchoring pallet racks to the concrete floor to keep them from turning over, and also for hanging pipe or hardware onto ceiling and parking garages using threaded rod and pipe hangers. Basically, the first two steps for wedge anchors and drop-in anchors are the same. You would first need to drill a hole into the concrete using a hammer drive drill and an SDS drill bit, which is specifically made for drilling into concrete. Next, you would need to blow out the hole to remove any dust or debris. Here's where things get different. A wedge anchor will be dropped into the hole, and once the nut is assembled and tightened on, it'll start to pull back on the anchor. However, this won't happen due to the expanding disc at the bottom of the wedge anchor, which bites into the hole and thus anchoring it into the concrete. In contrast, the drop-in anchor, considered by some to be the female version of the wedge anchor, would be dropped into the hole and then set by using a hammer and a pin-like setting tool that comes with the drop-in anchor kit. Once set in place, the drop-in anchor is now permanently locked flush into the concrete. A hex bolt would then be used to anchor a piece of equipment into the drop-in anchor. Although both wedge anchors and drop-in anchors are permanent, drop-in anchors are slightly less intrusive as they sit flush into the concrete. And in the case if the machinery ever needs to be moved somewhere else, you won't have an anchor sticking out of the slab and creating a tripping hazard. Although both of these items are sold in boxes roughly the size of your fist, wedge anchors come with nuts and flat washers and are commonly found in carbon steel with zinc or hot dip galvanized platings, as well as in stainless steel. On the other hand, drop-in anchor kits come with a setting tool and are usually available zinc plated and also in stainless steel. Although a wide variety of applications use these type of anchors, commercial contractors and mechanical contractors, which are those who install HVAC systems and plumbing into commercial buildings, would definitely use a lot of these types of anchors. Other types of anchors include hammer drives, which is a small nail-type anchor that once the pin is driven inward, the part that is inside the hole rapidly expands, thus locking it into place. Sleeve anchors, which function essentially the same way as wedge anchors do. Tapcons, which are masonry screws used for drilling into brick and concrete. Possible applications would be to hang wooden boards on a brick wall. In addition, we mentioned earlier about SDS bits. Since you first need a hole, these drill bits are required when installing drop-in anchors and wedge anchors. Therefore, always ask customers, do you need an SDS bit when they are buying wedge anchors and drop-in anchors? Another type of permanent anchor is the epoxy or chemical anchor. They come in different forms, which basically forms a glue in which a piece of threaded rod is inserted into the hole while the glue is still wet. Once it dries, it's not coming out. An epoxy, by definition, is a two-part adhesive that once mixed together forms a very strong bond. Of course, all of these first start with a hole being drilled by an SDS drill bit. Epoxy cartridges come in a variety of types of dispensing methods. Some will fit with a standard yet heavy-duty caulk gun, where other brands would require an expensive double-chamber gun. Chemical anchor capsules are also another way that epoxies are installed, in which the user drops a test tube-looking capsule into a hole. The tube is then broken when a piece of threaded rod or rebar is hammered into the hole, thus mixing the epoxy together. Next, we will discuss eye bolts. Eye bolts come in a variety of different types. The picture on the left shows a turned eye bolt, in which it is made from one piece of metal that is threaded on one end and then turned on the other end to form an eye. The next eye bolt is a non-shouldered eye bolt. It doesn't have a shoulder like the two eye bolts on the right. Nevertheless, shouldered eye bolts are also called lifting eye bolts, as they are often used to lift equipment such as gearboxes and valves. It should be noted that eye bolts were designed to lift equipment straight up and down, and are much weaker when the force lifting them is at any other angle. Cousins to the eye bolt would include the eye lag screws, eye nuts, and rod ends. Eye lag screws are essentially turned eye bolts with lag screw thread. These are commonly found around the house when used to hold up swings to wooden awnings. Eye nuts can be threaded onto any externally threaded part, thus creating a point where rigging can be used to lift an object. And lastly, rod ends look a lot like eye bolts, but are used in a variety of different applications, but primarily used to lock tank and vessel doorways. Most rod ends are custom, as they can come with or without a hole. In addition, the length of the rod end are measured from the inside of the hole, or would-be hole, to the end of the threads. U-bolts are typically used for attaching pipe to a support post. Other common applications is to hang wrought iron pipe in mechanical applications such as drainage and fire protection piping in commercial buildings. Oddly enough, U-bolts are measured by the pipe size that they intend to hold, and are available in different stock, which is their diameter sizes. U-bolts are typically found in carbon steel with zinc or hot-dip galvanized platings, and are also available in stainless steel. You should notice that the length of U-bolts are actually measured from the inside of the U. In addition to the standard patterns, they are also available in longer lengths, called Schedule 137 or long tangent patterns. Click on the link below to watch a video of how Portland Bolt makes large diameter U-bolts. Some U-bolts can be dipped in neoprene to give a better grip to the pipe that it's holding. Other common requirements for U-bolts include that they have 4 nuts attached, and possibly a backing plate. J-bolts are J-shaped fasteners that are primarily used as a type of anchor. Applications include J-bolts being used in the aggregate and mining industry to hold shaker screens down in place. Important dimensions include the diameter, the length, which is measured from inside the J to the end of the threads, and the length of the hook, which is measured from inside the J, and also the length of the required threads. Although J-bolts can easily be made in custom sizes, stock sizes are often found in carbon steel, plain finish, and zinc finish, as well as 304 and 316 stainless steel. Socket products is the next type of externally threaded fastener in which we will cover. This group includes a large variety of products that share a common similarity in that they all have an indented hex known as a socket type drive. Most plain finish socket screws are actually made of an alloy steel that has similar mechanical characteristics or strengths to a grade 8 material. Therefore, the strength of a socket set screw or socket cap screw allow them to be better suited in holding machinery and industrial equipment together. Socket head cap screws, sometimes called hex socket cap screws, have a cheese block shaped head that is often available in an alloy steel and stainless steel. The available sizes of socket head cap screws range from very small to extremely large. Flat socket cap screws are quite similar to socket head cap screws. However, the flat shaped head allows it to be countersunk, thus being flush with the surface that it's screwed into. Socket set screws are small, headless screws that possess a socket type drive. Socket set screws can have several different types of points. Although the most common point is the cup point, other points like cone point, half dog, and full dog exist. Socket set screws are almost always small in diameter and are commonly used in mechanical seals. The different types of patterns listed here are important and should be memorized. Square head set screws, although not technically a socket product, are often referred to as jack bolts. These screws have square heads and are fully threaded, thereby allowing them to be useful in leveling and adjusting machinery. Button socket cap screws are also very similar to socket head cap screws, except that they have a truss-shaped head and are not as common and are usually only available in smaller diameters. Socket shoulder bolts are fairly weird looking, since most of the bolt is actually its shoulder. In fact, shoulder bolts are measured differently than other fasteners, since only the diameter and the length of the shoulder is considered. Therefore, as far as measuring is concerned, the threads on the end of the bolt should be ignored. Socket shoulder bolts are often used in heavy equipment in which its large shoulder is bearing the brunt of the weight of the component being fastened together. I must admit, socket pipe plugs look almost identical to socket set screws, in which they are headless and have an indented hex for a drive. However, the difference is that socket pipe plugs are made with pipe thread. We'll talk more about this later, but National Pipe Thread, known as NPT, does not mate with any type of fastener. It's a different type of thread. Therefore, even if you tried, you wouldn't be able to put a half-inch nut onto a half-inch socket pipe plug. Again, because the nut is made of UNC or UNF type threads, and the pipe plug has NPT threads, they're simply incompatible. Oil and air lines that enter and exit machinery is usually tapped with pipe thread. Therefore, if you want to plug up one of these holes, you would probably use a pipe plug and not a set screw. We are now about to cover smaller screws. Most people get bogged down with the endless varieties that exist. However, if you can identify a screw by three things, you'll have most of these bases covered. The three things you need to know is the head type, which basically describes the shape of the head, the drive style, which is how does the screw turn, and three, the type of screw it is. Is it a machine screw? Is it a lag screw? Is it a sheet metal screw? Is it a deck screw? After you know these three things, you should be able to identify exactly what type of screw it is. Before you is many common types of head styles. The 10 styles in front of you are not all of them. However, it does encompass the most common ones. I'm going to suggest that you memorize these, and when you're ready, click Continue. As I discussed, the drive style describes the pattern to which the tool, for example the screwdriver, fits the screw. Most common drive styles include slotted, Phillips, posi drive, Torx, and an indented hexagon shape, which we just covered in all socket products. Lastly, the third aspect of identifying a screw is to realize what type of screw it is. Is it a machine screw, meaning that it is designed to mate with a nut or thread into a tapped out hole? Or is it a wood screw, a deck screw, or a lag screw, thereby being designed to drill into wood? Or is it a sheet metal screw, in which it is designed to possess a really sharp point? However, not to be confused with a tech screw, also known as a self-drilling screw, which has a drill bit-like tip. Although both sheet metal screws and tech screws are designed to drill into metal, tech screws are often mated with rubber neoprene washers, which allow them to hold roofing and metal siding onto metal buildings. These screws come in a rainbow of different types of colors, and since it is paired with the neoprene washer, it creates a leak-proof seal, thereby preventing leaks when it rains. Similar to most externally threaded fasteners, a screw's dimensions are identified by their diameter, their thread pitch, and also their length. It is very important to understand that a number 14 screw is exactly the same thing as a 1/4 inch diameter screw. However, it is equally important to realize that this is the only correlation, making a number 12 the next smaller size than a 1/4 inch, and progressively a number 10, number 8, number 6, and number 4 even smaller. And also similar to many other externally threaded fasteners, the length is measured from under the head, unless it has a flat head, in which it is measured by its overall length. Remember, in order to properly identify a screw, you must know the type of head, the type of drive, and the type of screw. Let's practice identifying some of the screws listed before you. We have now completed identifying the most common types of externally threaded fasteners. So now let's discuss the types of internally threaded fasteners. Strangely enough, nuts come in an immense number of different patterns. However, the most common types include the finish pattern and a heavy pattern. Finish pattern nuts would consist of your everyday, light-duty, and off-the-shelf nuts. Although they can come in a full gamut of materials and platings, but the most common finished nuts are found in bolt bends are grade 2, grade 5, grade 8, and 18/8 stainless steel. In addition, a rule of thumb exists is that light coating should always be mated together. Therefore, it's not recommended to mate a hot dip galvanized nut with a stainless steel bolt. Heavy hex nuts are both thicker and wider than a same size finish nut. These nuts are available in many different types of materials and are also typically used for large diameter and high strength bolts. We will soon show you nut compatibility charts which will help in determine which grade nuts are to be mated to a specific grade of bolt. Nuts that are 7/16 inch in diameter and smaller shall be double chamfered, where larger sizes are either double chamfered or chamfered on one side and with a washer face bearing surface on the other. Heavy hex nuts are considered stronger than any other equally graded nuts because of its greater length of thread engagement and a greater resistance to dilation, which is the widening or stretching of a nut. Grade A nuts are used with low carbon heavy hex bolts, while grade C nuts are recommended for use with A325 structural bolts. It is important to realize that grade 2H nuts are heavy hex nuts that are recommended for use with bolts in high pressure such as B7 studs. Grade 2H nuts are also acceptable to be used on A325 structural bolts. Grade DH nuts are recommended for use with A490 Type 1 structural bolts as well, where grade DH3 nuts are to be used on A490 bolts that are Type 3. And if I haven't thrown enough at you already, this is important. Grade 8 nuts is an ASTM A194 specification for stainless steel heavy hex nuts. This shouldn't be confused with the SAE Grade 8 hex cap screws in the nuts that are commonly found in a zinc yellow coating and in bolt bends. At the end of the day, we want you to know that there's two most common heavy hex nut specifications. They include ASTM A194 and A563. We will now discuss both of these specs in further detail. This chart includes several of the different grades and their corresponding markings that fall under the ASTM A194. Let's focus on grade 2H, 2HM, grade 8, and grade 8M. As previously mentioned, grade 2H is the grade of nut that is to be made with B7 studs, and is also acceptable nut for A325 structural bolts. However, to get a grade 2HM, you must reheat treat the nut. The M in this case means modified. When inspected, the appearance of a 2HM nut and their corresponding B7M studs appear that they've been burnt. That's because technically they have been. The oils that existed on the surface of a 2H nut and the corresponding B7 studs turned into an ash-like consistency once heat treated. As mentioned on the previous slide, ASTM A194 Grade 8 nuts are an equivalent to a 304 stainless steel, and the ASTM A194 Grade 8M nuts is equivalent to 316 stainless steel. So as previously stated, fasteners are highly engineered products. Thereby, it is important to match the correct nut with the bolt that was chosen for a particular application. This nut compatibility chart listed here is an important tool and should be memorized. Similar to ASTM A193, ASTM A563 covers chemical and mechanical requirements for carbon and alloy steel nuts. This chart addresses grade marking requirements and mechanical requirements with these nuts. We will discuss further information on suitable nuts for various grade of bolts very shortly. However, the take-home message here is that ASTM A563 nuts that are made from cheap carbon steel are considered a grade O or grade A. As you see, the minimum proof load on these nuts are substantially less than other nuts. Also, it is important to realize that grade O, grade A, and grade B nuts do not need to be marked with a grade. According to the A563 specification, the requirements for any grade of nut may, at the supplier's option and with notice to the purchaser, be fulfilled by furnishing nuts of one of the stronger grades specified here, unless a substitution is not allowed in this inquiry or purchase order. This is important because some grade nuts are not readily available in certain sizes and finishes. Additionally, the specification allows for the substitution of ASTM A194 Grade 2H nuts in lieu of ASTM A563 Grade DH nuts due to the lack of availability of Grade DH nuts in nominal sizes from 3/4 of an inch and larger. Please realize that hot-dip galvanized nuts are actually tapped oversized to compensate for the thick hot-dip galvanizing plating on the threads of the externally threaded fastener. Based on the previous slide and this nut compatibility chart here, things might get a little bit tricky, but don't worry, this is really for reference purposes only. What beginners should realize is that the nut that is to be used is actually based upon what bolt is being used. Nut compatibility charts like the one shown here are used to make these decisions easy. The next type of internally threaded fastener we will discuss is the hex jam nut. Jam nuts, sometimes called as half nuts, are thinner than a standard hex nut, but have the same dimensions across the flats and corners. Hex jam nuts are commonly used as a lock nut. To do this, two nuts are used. First, A separate nut must be assembled onto a bolt. Then, a jam nut is threaded against the first nut, which will subsequently lock the first nut in place and prevent it from backing off, thereby creating a locking effect. The next type of nut we will discuss are lock nuts. Lock nuts come in a huge array of different patterns. However, what they all have in common is that they have some sort of intrinsic element that creates friction when assembled onto an externally threaded fastener. Nylon insert lock nuts, or nil nuts for short, have a small piece of nylon forged into the top of the nut. This nylon hangs over just enough so that when a bolt is threaded into the nut, the threads of the bolt dig into the nylon, thus creating a large amount of resistance. Nylon lock nuts are fairly inexpensive and are very common in maintenance-type bolt bends. Similar to the mechanical workings of a nylon insert lock nut, an all-metal lock nut, also referred as Grade C, stover nuts, lacks this piece of nylon and simply has its head bent down further. Thereby, instead of plastic, you actually have the metal of the lock nut rubbing against the threads of the bolt. Flange nuts are another popular lock nut that look like a standard nut but with only a flat washer forged onto the bottom. Flange nuts are also available with serrations and non-serrated. During the manufacturing process, the opposite sides of the hex are squeezed inward just enough to turn the circular shape of the inside diameter into a slight oval shape, thereby creating enough resistance when assembled onto a bolt to make it difficult to get on or off without a wrench. Keps nuts, which are typically only available in smaller sizes, have an external tooth lock washer affixed to one side of the nut. This design of the Keps nut allows the nut to be generating a force that is perpendicular to the surface that it is fastened against. This will help in keeping the nut from backing off, thus creating a lock nut. Other lock nuts, like slotted nuts and castle nuts, require a cotter pin to be used. This cotter pin is inserted through a drilled hole through the diameter of a mated bolt and is bent between the slots of the nut to ensure that it will not back off the bolt. We will now move on from internally threaded fasteners to non-threaded fasteners. The first type we will cover are flat washers. Similar to nuts, flat washers are a very common commodity. However, unlike most other fasteners, flat washers are often sold by manufacturers by the 50-pound box. The only dimensions needed to fully identify a flat washer is its ID, or inside diameter, its OD, or outside diameter, and its thickness, and of course the material that it's made from. Fortunately, the USS and SAE pattern are two very common styles that exist to make ordering flat washers easy. Although it may be a little bit difficult to imagine from these pictures, the primary difference between the two is that the USS pattern has a larger outside diameter than the SAE pattern. Imagine it this way. SAE stands for the Society of Automotive Engineers, right? Thus, this pattern more commonly goes on automotive and heavy equipment. If you're bolting down an alternator onto an engine block, you wouldn't want this enormous washer that might not even fit into place without bumping or beating into something as it slides down. So it was determined that it would be useful to have a flat washer with the same ID but a smaller outside diameter. Therefore, the SAE flat washer was created. It should be noted that these washers here are most commonly found in Grade 2, Grade 5, and Grade 8. Also, most stainless steel washers are typically closer to the SAE pattern than the USS, most probably because it takes less material for an SAE pattern and thereby is less expensive. Here's a chart that compares the dimensions of SAE and USS flat washers. For simplicity's sake, let's compare the differences for a 1-inch USS and SAE flat washer. As you see, the inside diameter is 1.062 inches wide. So why isn't it exactly 1 inch wide? If the ID was exactly 1 inch and the diameter of the bolt was exactly 1 inch, the bolt wouldn't fit through the washer. In fact, they would actually be the exact same size, thus simply butt up against each other. On the other hand, when we compare the outside diameters of the USS flat washer to that of the SAE flat washer, you will notice that a SAE flat washer is a ½ inch shorter in width. Although the USS pattern is probably the most common pattern of flat washer, fender washers and F436 structural washers are fairly common as well. Fender washers differ from other washers in that the outside diameter is even larger and is actually stated at time of order. For example, you would be able to order a 5/16 by 1 fender washer and also a 5/16 by 1.25 inch, whereas 5/16 reflects the nominal ID and 1.25 inch is its outside diameter. In the structural steel market, ASTM F436 structural washers are extremely common. These washers almost mirror the dimensions of the SAE pattern. However, F436 washers are through hardened, thus making them ideal to be used with A325 structural bolts. The next type of washer we will discuss is the lock washer. Although we'll keep our discussion on lock washers brief, the most common type of lock washer is the split or helical split lock washer. In recent years, the Nordlock lock washer has made its debut on the fastener scene. Although they're fairly expensive, they are excellent for use in environments that may be subject to a lot of vibration due to the fact that it takes approximately 20 to 30% more torque than what was used in the assembly to take the nut off. Other common types of lock washers include the internal tooth lock washer and the external tooth lock washer. The next two types of washers are commonly confused by beginners. This is probably because they both begin with B and sound similar. However, they are very different. Bevel washers are commonly used in structural applications, primarily to compensate for the lack of parallelism when a fastener is being tightened together. However, Belleville washers are also known as conical spring washers and are highly engineered washers. These actually act like springs and apply a preloaded force to a bolted joint. Belleville washers can come in a wide variety of shapes, materials, and load strengths. As seen in the picture on the bottom right, when properly stacked and installed, Belleville washers will indicate to the operator the amount of tension when tightening, as well as any loss of clamp force during the lifetime of this joint. As we continue to cover some of the more common non-threaded fasteners, this category includes rivets. Rivets come in a wide variety of different head styles, shapes, and also different materials. However, the most common include aluminum, steel, and stainless steel. Click on the link below to watch a video as to how rivets work. Illustrated here are the many dimensions of a standard pop rivet. Rivets are indicated as 2 or 3 digit size numbers that actually describe the diameter and length of the rivet. The first number indicates its diameter in 32nds of an inch. Therefore, a size 8 is 8/32nds of an inch. Rivet gauges like this one are important to help you quickly identify the size of a rivet. You simply put the head of the rivet into the cutout on the right to determine the appropriate diameter, and then measure from under the head to the end of the body to determine its length. The length of the rivet determines its maximum grip capacity. The latter number of the size indicates the length of the rivet in 1/16 of an inch. Therefore, a 54 rivet would mean that its diameter is 5/32 and its length is 4/16, which of course is a 1/4 inch. Other non-threaded fasteners include U-drives, which are essentially tiny little screws that are hammered in holes. U-drives are most commonly used to hold serial number tags and ID tags onto equipment. A cousin to the rivet would most probably be the riv nut. Riv nuts, like rivets, require the use of a gun to assemble them into place. Truck repair facilities commonly use riv nuts on the panel walls of 18-wheeler trailers. Once a riv nut is inserted into the paneling, a bolt then can be used to hang or fasten something into that panel. Maintenance and repair shops commonly have stacks of pull-out drawers that often include small items like cotter pins, hitch pins, internal and external snap rings, and grease fittings, which are also known by some as alamites or zerks. These also include roll pins, which are commonly known as spring pins. These pull-out drawers can oftentimes have electrical terminals, screws, and other small brass and DOT fittings. Electrical terminals are commonly found in different types of colors. These colors actually identify for the different sizes of wire that will fit these fittings. The smaller terminals, which are red, are made for wire gauges size 22 to 18. The blue terminals are made for wire gauge size 16 to 14, and the yellow fittings are made for wire size gauges 12 to 10. Note that the smaller the wire gauge, the larger the diameter. Although clear nylon and vinyl are the most common types of terminals, heat shrink terminals are also available, and including non-insulated and terminals made for high temperature. This chart reflects some of the most common electrical terminals used. These include bullet connectors, butt connectors, push-on terminals, ring terminals, spade, also called forks, wire pin terminals, also called ferrules, and X and Y configuration connectors. The picture at the bottom right represents what a lot of these pull-out drawers look like. Click on the video link to the right to learn more about electrical terminals. Here is a small selection of the different types of fuses. Most commonly found in truck repair shops are ATC and ATO fuses, mini fuses, maxi fuses, cartridge fuses, the old school AGC fuses, as well as a few other types. Other types of non-threaded fasteners that are commonly found in pull-out trays include cable ties. Cable ties are a very versatile type of fasteners that come in other forms, but most common sizes include 4-inch, 6-inch, 8-inch, 10-inch, 12-inch, and 15 inches. Although they are most popular in black due to their ultraviolet light resistance, they are also readily available in different colors. Other items that are popular in heavy equipment and truck repair facilities include hose clamps. Hose clamps are commonly identified by a size number, like for example a size number 10 or size number 36. Hose clamps exist in several configurations, including having a zinc-plated clamp with a zinc-plated screw. You can also get them with a stainless steel clamp and a carbon steel screw, or an all-stainless clamp and screw configuration. Heat shrink tubing and electrical tape is also quite common as well. Both of these items work to prevent moisture and water from entering a splice connection. Other items that are commonly found next to fastener bends are pipe fittings. In my opinion, pipe fittings are sometimes a little bit easier to understand than fasteners, as they come in fewer different diameters. In addition to pipe nipples, which have tapered threads on both sides, the other fittings are listed here. These include couplings, crosses, plugs, elbows, which are commonly found in a 90-degree, a 45-degree, and a street elbow, caps, bell reducers, unions, hex bushings, and T's. Let's first discuss the different types of pipe fittings. These are classified according to their class number, like class 150 or 300 pound, 3,000 pound, or 6,000 pound. This correlates to a thickness of how thick the pipe fitting is and is directly proportional to the amount of pressure that it can withstand. Pipe nipples, on the other hand, are categorized by a schedule. A Schedule 40 is your everyday standard pipe nipple, whereas a Schedule 80 would be a more heavy-duty nipple. Both nipples and pipe fittings are available in a whole wide of different materials. Most commonly used are carbon steel fittings that are found in plain and hot-dip galvanized coatings. Stainless steel is also available in 304 and 316, and also brass and bronze fittings are quite common as well. It should be noted that pipe nipples are actually made through two different methods, with one being welded and the other one being made from one solid piece. So sometimes customers actually specify whether they want them welded or seamless. The next chapter will include a lesson about the threads of threaded fasteners. There are many different types of threads. However, in the U.S. fastener market, the imperial system, also known as the inch, is the most common. Throughout the rest of the world, the metric system is primarily used, thus explaining, for example, why steel mills with German-made equipment would use so much metric bolts on maintaining their equipment. Another common thread type is NPT, or National Pipe Thread. We have mentioned earlier in this tutorial that pipe thread, although it may look similar to the threads on fasteners, will not mate with each other and only work with pipe. Pipe is sized by the ID of the pipe, and fasteners are sized by the OD of the bolt or the ID of the nut. So it's kind of similar how nothing on a 1-inch U-bolt actually measures 1 inch. In fact, nothing on a 1-inch pipe plug actually measures 1 inch either. Now, let's discuss the basic elements of threads. The crest is considered the highest point of the thread, whereas the root is considered the bottom of the thread. Using these two terms, you can then measure the major diameter, which is the diameter measured between from crest to crest, and the minimum diameter, which is measured from root to root. The pitch diameter is actually the average between the major and minimum diameter. To the right, you'll see the difference between pitch and threads per inch. A thread's pitch, which is technically used more in the metric system, is the distance between two adjacent threads. In the inch system, threads are typically compared by their threads per inch, or TPI. It's relatively easy. You simply measure an inch and count how many threads are within that inch. As previously mentioned, the metric system refers to the thread pitch, which is the number of millimeters between the adjacent threads. There are three most common thread series available in the inch system for industrial fasteners. Unified National Coarse, which is UNC, is most popular. UNF, Unified National Fine, and 8 thread. Let's first talk about coarse thread. Coarse threads have fewer threads per inch than fine thread. Coarse thread bolts are more often used in the construction industry because they allow for more rapid assembly and are more resistant to damage from handling or corrosion, and lend themselves to thicker corrosion-resistant coatings. In addition, coarse threads also provide great resistance to internal thread stripping, and because of this are often used with relatively low-strength material. In contrast, fine thread bolts are more often used in original equipment manufacturers known as OEM type applications. These would include automotive and heavy machinery. Since fine threads are stronger and more resistant to vibration loosening than coarse threads, but are more susceptible to damage and cross-threading. This chart shows you the different threads per inch for 1-inch diameters and below. It is highly recommended that you be very familiar and practically memorize the number of threads per inch for the coarse thread column. Keep in mind that the previous chart only went up to 1 inch. For diameters that are 1 inch and larger, there are actually 3 thread series that exist: coarse thread, fine thread, and 8 thread. The 8 thread series is characterized by 8 threads per inch, regardless of the diameter, and is generally used on diameters 1 inch and larger. 8 thread is most commonly used on stud bolts and their corresponding nuts. So whenever handling studs, make sure you understand whether the customer wants coarse thread, fine thread, or 8 thread. The 8 thread series is also used where the engineer is looking for a compromise between coarse and fine thread series. 8 threads per inch are more resistant to vibration loosening than coarse thread. We previously talked about thread pitch and also threads per inch. Now we will actually talk about the thread fit, which is a measure of the looseness or tightness of mating threads. For unified inch threads, there are 3 different thread classes that exist. For external threads, 1A, 2A, and 3A, and 3 for internal threads, 1B, 2B, and 3B. All of these are clearance fits, which indicate that they assemble without interference. As a general guideline, the higher the class number, the tighter the fit. For example, an assembly which mates with class 1A and 1B threads will have a much looser fit than the assembly having a class 3A and 3B threads. Classes 1A and 1B are not very commonly used, but they do have their applications. They are ideally suited for quick assembly and disassembly and are a key consideration in design. Class 2A and 2B are actually the most common thread classes in use. This is typically all of your off-the-shelf type fasteners, offering a balance of ease of manufacture cost and performance. Class 2 threads hold a tight tolerance than Class 1, but not as tight of a class tolerance as Class 3. Class 2 are also the most common thread class used in the construction fastener industry. Most common ASTM construction fastener specifications require a Class 2 thread fit unless otherwise specified. Class 3 require the tightest tolerance and are usually used in applications where thread fit and/or accuracy are critical. Class 3A and 3B are best suited when close tolerances, safety, and strength are required. Thus, they are frequently specified for socket head cap screws and also socket set screws. You should understand that in the metric system, up to 4 thread classes actually exist for the same diameter. So, in conclusion, always ask to be certain that you understand what type of threads the customer is wanting. Bolt gauges are inexpensive tools used to identify a fastener's diameter, type of threads, and length. To measure a bolt, you will first put the bolt in the corresponding hole. One side is standard and the other side is metric. Prior to putting a bolt into the hole, I would suggest to look at the head of the bolt. The marking on it will usually tell you what grade or class the bolt is, thereby telling you whether it's metric or standard. Secondly, you would need to determine the length of the bolt. As previously mentioned, the length of bolts and hex cap screws are measured from underneath their head to the end of the screw, while items that are countersunk and have a flat head are measured from the overall length. To identify the size of a nut, you would use the post on the side of the bolt gauge. A coarse thread nut will only go halfway down the post, while a fine thread nut will go all the way to the bottom of the post. Lastly, there are grooves on the back that indicate the many different types of threads per inch and thread pitches. Therefore, by using a bolt gauge, you should be able to properly identify most fasteners by their diameter, threads, and length. As you see in the example above, we would state a hex cap screw by its diameter, thread pitch, and length. So, a 1/4 inch, 20 threads per inch by 1.5 inch hex cap screw grade 5 zinc plated. Or, for the nut, you would say the diameter, the threads per inch, and then the type of product it is, like a 5/16, 18 threads per inch jam nut made of 18/8 stainless steel. So how exactly are threads made? Threads can be produced by two different methods, cutting or rolling. Let's discuss them both more in detail. To create threads by cut threading, you are physically cutting, thus removing metal to create the threads, and thereby creating shavings. When cut threading, the size bar you will use is the nominal size bar. So if you're making a 1 inch diameter bolt, you would be using 1 inch diameter bar, which actually measures to 1 inch. The appearance of threads that have been made by cut threading is that the threads can sometimes feel sharp. The cutting tool is simply removing metal to produce the root or the bottom of the threads. In roll threading, it's completely different. The threads are actually squeezed on with lots of pressure. This process is similar to what would happen if you squeeze a banana. Where your fingers touch the banana, you create the root of the threads. And the crest of the threads is between your fingers, which is where the banana squeezes out. In contrast to cut thread, which you would start from nominal diameter bar, for roll threading you must start with pitch diameter bar, which as we explained previously is the average of the major and minor diameter of the threads. For example, the diameter of a 1 inch pitch diameter bar is actually 0.9 inches, not 1.0 inches. Thereby, once roll threaded, the major diameter is 1 inch and the minor diameter is 0.83 inches. Some of the advantages of cut threading is that there's fewer limitations with regards to diameter and thread length. Practically all specifications can be measured by cut thread. Disadvantages of cut threading is that there's significantly longer labor times, meaning higher cost. Here we will describe some of the definite advantages of roll threading. First of all, it's faster. So your standard grade 5 and grade 8 hex cap screws were definitely produced on huge production runs that use roll threading to create the threads. Another advantage is that because a roll threaded bolt has a smaller body diameter, it actually weighs less than a full bodied counterpart. This weight reduction reduces the cost of the steel, galvanizing, heat treating, plating, and freight, and any other costs associated with the fastener that are based on weight. Another advantage is that cold working makes threads more resistant to damage during handling. Rolled threads are often smoother than those made via cut thread. However, one more of the more important advantages is that the threads are actually even stronger. Here are two microscopic drawings that is comparing the grain structure of the threads. The grain structure on the fasteners that have been roll threaded have simply just been moved around and displaced. This is actually very important. Similar to the grains in a piece of wood, it is a point of weakness. It is more prone to breaking if the grains are disrupted, thereby making products that have been roll threaded to have stronger threads than those that have been cut threaded. It should be noted that roll threading does have some disadvantages. For example, the availability of pitch diameter bar can sometimes be hard to find. A325 and A490 structural bolts cannot be produced with the reduced body diameter. Here are links to two separate videos to show you how threads are made via cut thread and roll threading. Fasteners are manufactured in a wide range of materials from common carbon steel to titanium, plastic, and other exotic metals. Many materials are also further separated into different grades, describing their specific alloy mixtures and also their hardening process. Our next chapter will cover the different materials that fasteners are commonly made of. Since their conception, Fastener materials have always had a give and take in place in which engineers would need to ensure that the material is strong enough for the job, but yet would be able to resist the corrosion in its operating environment. For example, a grade 8 hex cap screw is definitely stronger than a stainless steel hex cap screw. However, if a fastener's purpose was intended to hold hardware onto a dock, the grade 8 bolt would probably quickly rust and eventually fail upon the corrosive environments of salt water, whereas a stainless steel fastener would not rust and would be much better suited for the application. Due to these facts, metallurgists design new super and exotic alloys that offer very high strength but also have a very high resistance to corrosion. Most of these alloys have proprietary names like hastelloy, Inconel, Alloy 20, and Monel, and are very expensive due to the high price of the base materials such as nickel. Common carbon steel grades used for fasteners are AI, SI, 1010 through 1022. Low carbon steel is used to make grade A307 and grade 2 hex bolts. Although A307 should be stamped onto the head, if there is no marking, it can be assumed to be a low carbon steel and relatively very weak. A medium carbon steel that is hardened through quenching and tempering can be made into a grade 5 hex cap screw or an A325 structural bolt, for example. As you see, the tensile strength, which is the amount of pressure at which a bolt will break, is nearly double that of the low carbon steel. Next, we will discuss the different alloy steels, but let's first identify what is an alloy. By definition, an alloy means a mixture. Therefore, an alloy steel is a steel that has been alloyed or mixed together with a variety of different elements to improve its mechanical properties. Alloy steels are broken into two different groups, low alloy steels and high alloy steels. The difference between the two is somewhat arbitrary, but many define it as 8%. Most commonly, the phrase alloy steel refers to low alloy steel. Technically, every steel is an alloy, but not all steels are called alloy steels. Even the simplest steels, which would be composed of 99% iron and 1% carbon. However, the term alloy steel is the standard term referred to steels with other alloying elements in addition to carbon. Common alloyants include manganese, which is the most common one, nickel, chromium, moly, vanadium, silicon, and boron. So going back to the topic at hand, alloy steel fasteners are made from a high-strength steel alloy and are further heat-treated to produce very high-strength fasteners. Common examples of these would be grade B7 studs, grade 8 hex head cap screws, and socket head cap screws. The next material we will discuss is stainless steel. The most common commercially available grade stainless is 304 stainless, which is part of the 188 stainless steel family. Albeit, most of the material numbers in the fastener industry seem kind of complex and arbitrarily assigned. However, 188 stainless actually stands for its 18% chrome and 8% nickel composition. I would like you to memorize the different grades of stainless steels listed here. To make it easy to remember, we have broken them down into two different categories. Commercial grade stainless, which is the most common found throughout the stainless steel industry, and marine grade stainless, which is more expensive and more commonly used offshore and in saltwater environments. It is important to remember that 304 stainless, 188 stainless, B8, and A2 stainless steel are practically the exact same thing. 304 and 188 are simply used more on SAE specifications, where B8 is referred to by ASTM specifications, and A2 is referred by the metric world. On the other hand, marine-grade stainless steels are referred to by several synonyms as well, such as 316 stainless steel, B8M, and A4. Again, these are practically the exact same thing. It's just that the SAE specification may refer to 316 stainless, whereas ASTM calls it B8M, and the metric world calls it A4. Again, this list should be memorized. It is a common misconception that stainless steel is stronger than regular steel. In fact, due to the low carbon content, stainless steel cannot be hardened. So when you compare the tensile strengths of stainless steel to that of carbon steel, you will find that stainless steel is stronger. However, when you compare stainless steel to mild or alloy steel, it is significantly weaker than hardened steel. So the take-home lesson is, stainless steel, just because it's stainless, doesn't mean that it's better than carbon steel. It has to do with the application that the bolt is being used in. The metric world refers to the different types of grades as classes. Therefore, let's compare the mechanical strengths of the most common metric classes to those of the common inch grades. The top half of this chart lists the tensile strength, yield strength, and the proof strength in megapascals, whereas the bottom is in psi. Let's look at the bottom, which is converted to KSI, which is thousands of psi. It is fairly easy to see that the tensile strength, which is defined as the minimum pressure at which a bolt will break, is relatively the same for a class 8.8 when compared to a grade 5. Also, the tensile strength of a class 10.9 is almost identical to that of a grade 8. And the class 12.9, which is often the socket head cap screws, is practically the same as the ASTM A574 for socket head cap screws. To analyze the strength of fasteners, a stress-strain diagram is very helpful. This data is plotted by a machine that pulls onto a bolt and plots its change in length. This science centers on the principle that fasteners are elastic and act exactly like springs. When they are pulled, they elongate. However, when the force relaxes, they return back to their original length. Note that there comes a point where the bolt is pulled too far and its spring-like or elastic properties are damaged. This point is called the yield point. Once a bolt is pulled past its yield point, it has entered its plastic phase, in which it will not return back to its original length. The point at which this change occurs is very visible on the graph. It is where the shape of the straight line starts to arc to the right. If the bolt is even pulled further past its yield point, it will eventually break. Therefore, the amount of force required to break a bolt is called its tensile strength. Once a yield point is determined, you can then calculate its proof load and its clamp load. The proof load is the greatest suggested load that a fastener should be tightened to avoid from reaching its true yield point, and that's typically calculated at 85 to 95% of the yield point. A fastener's clamp load, which is calculated at 75% of the proof load, is the suggested force that should be applied to a bolt. As you can see, a stress-strain diagram can ultimately give you a lot of information that is helpful in understanding the strength of fasteners. This stress-strain diagram compares the strengths of A307, grade 5, grade 8, and socket head cap screws. Try to see if you can identify each of the grade's yield point and tensile strength on the graph. Also, notice that once a fastener has been pulled past its yield strength, its diameter will start to get smaller and its length will get longer. This is very similar to what happened when you're baking and you're pulling apart bread dough. The amount of change in diameter and in length can be described to a fastener's reduction and elongation, in which we will discuss shortly. As you can see here, there is definitely a lot of science involved in the manufacturing of fasteners. For this reason, many customers' quality control departments require documentation, such as mill test reports and certificates of compliance, that prove that the fasteners were made upon their specifications and requests. Mill test reports, commonly referred to as MTRs, is a document that is created by taking a sample from the order and also analyzing its mechanical, chemical, and sometimes dimensional properties. Similar to the food and pharmacy industry, when fasteners are made, they are lot controlled, thus creating a lot number, and also when they are heat treated, a heat number. These numbers serve as a tool for the manufacturer in case of a quality problem should arise. A fastener's mechanical properties describe the intrinsic properties of the material. These include its yield strength, which is the amount of force required to permanently stretch a fastener where its spring-like properties are disrupted, its tensile strength, which is the minimum amount of force required to break a fastener, its elongation, which is a percentage that compares the change in length from the broken fastener to its original length, and its reduction of area, which compares the diameter of the broken fastener to that of the original diameter. Keep in mind that all of these materials vary in their ductility, which is their ability to be drawn into wire. Similar to Play-Doh, as you pull it apart, its diameter will get smaller and smaller until it simply breaks. Therefore, the reduction of area compares this change in diameter. Another common measurement in an MTR is hardness. Similar to temperature having different units like Fahrenheit and Celsius, there are different units of hardness which include Rockwell, Burnell, and Vickers. There is also a toughness test called a Sharpie impact test, in which a pendulum is crashed into the material. By measuring the dent, one can conclude the material's toughness, thus the amount of energy needed to fracture a material, which is directly linked to its brittleness. On the other hand, a certificate of compliance, or a CSC, simply states that the material was ordered to what they wanted. CSCs exclude all of the technical information that are available on MTRs. Here's an example of a mill test report. As you can see, many of the elements that we just discussed are available here. On the MTR, you will see that there is a purchase order and a sales order number, a description of the item, the lot number, its heat number, tensile strength, yield strength, elongation, reduction of area, and hardness. Below it, you'll also find the chemical composition of this alloy. Here are some additional videos that clarify the details of the tensile strength and the different types of hardness strengths. It is often helpful to understand the processes required to make fasteners. One of the first steps involved is to obtain the properly sized raw material. Then it needs to be formed into a shape, which is most commonly done by hot forging or cold heading. In hot forging, a piece of material known as a billet is heated, usually by induction heating, and then placed into the forging equipment once it is glowing red. This process is slow and usually done one piece at a time. On the other hand, cold heading machines, which actually operate at room temperature, just require a lot of pressure to change the shape of the metal, which is actually from spools of wire that is then cut immediately prior to cold heading. Once these items have been properly formed, threads are then created by either cut threading or roll threading. And depending on what is being made, other processes like heat treating and plating can take place as well. Click on the videos listed here to get a better idea of the processes involved in making fasteners. The next chapter we will cover is heat treating. One of the two main things the heat treating affects is a fastener's tensile strengths and hardness. Heat treating is a three-box process: annealing, quenching, and tempering. Let's look at this process in more detail. Metallic materials consist of a microstructure of small crystals called grains or crystallites. The nature of these grains, for example, the grain size and composition, is one of the most effective factors that can determine the overall mechanical behavior of the metal. Heat treating provides an effective way to manipulate the properties of the metal by controlling the rate of diffusion and the rate of cooling within the microstructure. Heat treating is also used to alter the mechanical properties of an alloy, changing properties such as hardness, strength, toughness, ductility, and elasticity. Click on the two video links below to get a better understanding of the heat treating process. The first process of annealing is to heat a material to a specific temperature above the high critical temperature and cooling it slowly at a rate that is controlled and that will allow the grains to organize and produce a refined microstructure. This relieves stresses and increases strength and ductility. The next process, quenching, is a process of cooling a metal very quickly. This is most often done to produce a martensite transformation. In ferrous alloys, this will often produce a metal that is harder, while non-ferrous alloys, this will produce something that's usually softer. Following quenching, you now have a part that is hard, however it is brittle. Similar to freezing a rose in liquid nitrogen, the rose is now harder, however if you tap it, it will shatter. Tempering this part will actually alleviate this problem. Most applications require that quenched parts be tempered. Tempering consists of heating steel below the lower critical temperature, often from 400 to 1100 degrees Fahrenheit. Now is a good time to point out two different terms regarding the fact that not all items harden the same way. Grade 5, Grade 8, and Grade B7 materials are examples of things that are through hardened. Similar to a marble, the hardness of a through hardened part is the same on the outside as it is in the inside. On the other hand, similar to how M&Ms have a hard candy shell with the soft center, some items are case hardened, in which the outside case is harder than the hardness of the core. This is seen with Class II stainless steel material, also known as strain hardened. Another example of case hardening is nitrate coated drill bits. If the drill bits are sharpened, the hardened case is actually removed, thus leaving a softer material behind. As we previously mentioned, fasteners are commonly protected by coatings and platings designed to lengthen their life by reducing effects of corrosion. By definition, a plating is the covering of an item by a metal. Although applied differently, zinc, cadmium, and hot-dip galvanized are all examples of platings. Additional coatings like PTFE, Teflon, or Xylane coatings are recognized by the industry as having a very superior resistance to corrosion. We will now go into detail as far as the processes of zinc plating, hot-dip galvanizing, mechanical galvanizing, and Teflon coating. Zinc is the most popular of all commercial platings because it is relatively economically inexpensive and offers good corrosion resistance in environments not subject to excessive moisture. Cadmium plating results in a smoother surface and greater resistance to white oxidation spots than zinc plating. However, since cadmium is more toxic than zinc, which makes the plating process more difficult and costly, it is less common. Electroplating is a method of depositing a metal onto the surface of another metal, such as steel. This is done by immersing the fasteners in an appropriate plating bath in known solution with a known electrical current. The zinc or cadmium travels through the electrolytic bath from the anodes and attaches to the surface of the fasteners. Although relatively thin, the thickness of the zinc or cadmium plating depends primarily on the time spent in the plating bath, the amount of current, and the chemical composition of the bath. The process begins by the parts first being cleaned in an acid bath, which is known as pickling. Once free of oil and contaminants, the parts are then immersed in an electrolytic bath and are zinc plated, and are then taken out after a calculated time. Following plating, the parts are typically dipped in a chromate type bath. This gives the parts a yellow or silver type color. Also realize that zinc and cadmium plating is a relatively very thin coating. We're not going to cover this in detail, but just let it be known that the thickness of the electroplated zinc and the color of the chromate coating isn't chosen by accident. Although some are more commercially available, specifications do exist to allow the order of more custom thickness and colors. As mentioned previously, a rule of thumb with coatings is that the thicker the coating, the better the protection. The process for hot-dip galvanized first starts off like most other coating processes, in that they are first cleaned. Although this can be done via a mechanical method like being sandblasted, pickling them in sequential acid baths is the easiest and fastest method available. Once cleaned, the parts are then submerged in a vat of molten zinc. Unlike electroplating, this bath is much thicker and it is not electrically charged. Once removed from the kettle, the parts are then put in a centrifuge and spun to remove any excess zinc. This is an important process as thick clumps of zinc that are left in the threads, thus rendering the bolt useless. Now with that being said, hot-dip galvanized provides excellent corrosion protection, however it does have its disadvantages. The main drawback actually is the thickness of the hot-dip galvanized coating. Thickness is commonly referred in mils, which is 1/1000th of an inch. Note that a mil is not to be confused and has nothing in common with the metric millimeter. Keep in mind that when a plating is referred to have a thickness of a certain amount, that thickness is coded all around the bolt. Therefore, if you want to determine the diameter of the bolt after it has been coated, you would add the original diameter of the bolt plus double the thickness of the plating. Typical thicknesses for hot-dip galvanized can range between 1.8 to 3.5 mils, which can make the standard bolt and nut tolerances very difficult to maintain for correct assembly. If bolts are galvanized, then the nuts should be oversized to accommodate for the 3.6 to 7 mils increase in bolt diameter after galvanizing. If this is not done, the assembly of the bolt and nut will become either impossible to assemble or will result in the hot-dip galvanized coating being scraped off the threads. Either scenario is unacceptable. To minimize this drawback, hot-dip galvanized nuts are retapped a slightly sized larger, known as overtapping. By overtapping galvanized nuts, this will remove the zinc coating along the inside of the nut and provide enough clearance for the hot-dip galvanized bolt to easily assemble onto the nut. Hot-dip galvanized parts are typically dark gray and quite coarse in appearance. Here I like to convey the difference in appearance that hot-dip galvanized has when compared to that of zinc-plated and stainless steel bolts. A different process, known as mechanical galvanized, utilizes a zinc powder in a revolving barrel, in contrast to the molten hot zinc that hot-dip galvanized offers. First, the parts are commonly cleaned by pickling and then loaded into a big revolving barrel. This barrel is loaded with small glass beads and a zinc powder, which amount has been calculated to match the total surface area of the parts for the desired thickness required. Since the glass beads are physically beating the zinc powder onto the fasteners, that is why this is called mechanically galvanized. The finished product has a thinner coating than hot dip galvanized, and it has a smooth, powdery feel to it. Fluoropolymer coatings will be the last coatings that we will discuss. It has grown in popularity over the past 20 years as the industries recognize its benefits. For example, the Teflon-based coating provides very superior protection against corrosion. Therefore, years can go by and the nuts can still be disassembled from the studs. This would be important in petrochemical plants that would need to change out a valve or pipe handling gasoline. No one would want to risk an explosion for lighting a cutting torch to cut apart the rusted out bolt and nut. It is common to have Teflon-coated commodities that are stocked for offshore and petroleum applications to include B7 studs and their corresponding 2H nuts, F436 washers, and B7 heavy hex cap screws. The process is different from others in that Teflon coating, in which after the parts have been cleaned, are electrostatically sprayed on a conveyor belt and then baked in an oven. Although commonly blue, Teflon coatings is available in a range of different colors and can be coated on practically any metal. Proprietary names of this type of coating include Fluorocoat 1, Whitford, Xylan, and also a whole different types of proprietary names. It is also important to understand that the thickness of the Teflon coating requires for the nuts to be overtapped. Therefore, if you try to fit a plain finished 2H nut on a Teflon coated B7 stud, you probably wouldn't be able to get it on, and if you could, it would definitely be a tight fit. This is another example of why you should mate light coatings with other light coatings. To be able to compare the corrosion-resistant properties of fastener coatings and platings, the salt spray test was invented. Currently, this test is the industry standard for accelerated corrosion testing of different metallic coatings. The samples are then inserted into the chamber, at which it is a temperature-controlled environment, and is sprayed with a 5% salt spray solution at a very fine mist. Here you will see the finished results of a 1,000-hour salt spray test. Notice that red rust has formed on the plain finish, cadmium-plated, and zinc-plated stud bolts. In addition, white rust covers the hot dip galvanized stud bolt, while the Fluorocoat stud bolt appears unharmed. Coating and plating processes occasionally do introduce problems. As discussed earlier, hot dip galvanizing when done sloppily will leave chunks of zinc in the threads, preventing nuts from being assembled. A bigger problem exists in the issue of hydrogen embrittlement, which can cause a bolt to become brittle and fail. This starts in the cleaning process when they are pickled in vats of acid. At this time, atomic hydrogen ions can be absorbed throughout the surface of the fastener. Once coated, the electroplated coating traps the hydrogen inside, unless they are baked soon after plating to drive out the hydrogen, known as relief baking. If the hydrogen remains in the steel, it can migrate to areas of high stress and cause small micro cracks, which rapidly will enlarge under load and subsequently causing a failure. Standards recommend relief baking for all fasteners above a hardness Rockwell C of 40. Therefore, high hardness parts such as grade 8 and class 10.9 fasteners are more susceptible to hydrogen embrittlement and should be relief baked after plating or coating to reduce the chance of hydrogen embrittlement from occurring.